Example 3 says, for what values of p does the integral from 1 to infinity of 1 over x to the p power dx converge? When it does converge, what is its value? So we actually need to break this up into two cases because in most cases we can integrate 1 over x to the p power by using the power rule, but not if p is equal to 1. So let's start off with that case. What if p is equal to 1? Let's see what happens. Then we're going to have the integral from 1 to infinity of 1 over x dx, and that's going to equal the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. That is equal to the limit as b approaches infinity of the natural log of the absolute value of x evaluated from x equals 1 to x equals b. And that's going to equal the limit as b approaches infinity of the natural log of the absolute value of b minus the natural log of 1, which is going to equal 0. And if you don't remember, the graph of the natural log function looks something like this. Here's the y-axis, here's the x-axis. Its x-intercept is at 1, 0, and it looks something like that. So it's unbounded on the top, which means that this is going to go off to infinity. So that's what happens if p is equal to 1. Now let's explore the case if p is not equal to 1. So if p is not equal to 1, this is what we have so far. I've gone ahead and I've rewritten my integrand as x to the negative p power so that it's easier to use the power rule for integrals. So I'm going to increase the power by 1, and then I'm going to divide by that new power. And I'm evaluating this from x equals 1 to x equals b. So anywhere I see an x, I want to replace it with b, and then with 1. So this is going to equal the limit as b approaches infinity of b to the power of negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 is just going to be 1. And then we have that. Now notice that these both have the same denominator, and p is not a variable with respect to the limit. So what I can do is I can factor out my denominator from both of these things, and I'm going to factor out 1 over negative p plus 1, but I'm going to rewrite that as 1 minus p. It looks a little bit nicer. And then we're going to have times the limit as b approaches infinity of, I'm going to rewrite this as 1 over b, and then I need to multiply the power times negative 1, so that would be p minus 1, and then minus 1 here. So take a minute, pause the video, and think about what you think this limit might equal. It actually turns out that this limit is going to change depending on what p is. So let's just think about, suppose p was negative 2. So here this would be 1 minus negative 2, and then that would be all over, or that would be the denominator for 1, and so that would simplify to 1 over 3. And then if p was negative 2 here, then this would change into 1 over b to the negative 3 power, which would change into b cubed minus 1, and then that would just go off to infinity. So it turns out that this limit is equal to infinity if p is less than 1. Now, suppose p is greater than 1. Remember, we're not considering the case when p equals 1 because we started off saying p does not equal 1. So we're considering the two cases if p is greater than 1 and if p is less than 1. Now, if p is greater than 1, what happens is this fraction right here is going to go off to 0. And so then I'm going to have 0 minus 1 times 1 over 1 minus p. And if I distribute that negative 1 into the denominator, that's going to be the same as 1 over p minus 1. So those are our two cases, and let's combine this and put this in a condensed manner now. So to condense what we have written, now we can say that the integral from 1 to infinity of 1 over x to the p power dx is equal to 1 over p minus 1 if p is greater than 1, and then it's equal to infinity if p is less than 1, or also the case if p is equal to 1. And that was from earlier, right here, when p was equal to 1. So that's why I added this to that. And so here we have our final example. So it turns out that the example that we just did is referred to as the p-test, and that's going to come up again later, so let's talk about it. More generally, if a is some positive constant, we can say that the integral from a to infinity of 1 over x to the p power dx converges if p is greater than 1 and diverges when p is less than or equal to 1. Note, the lower limit of integration must be a positive constant, and the numerator of the integrand must be 1. All right, let's switch topics now. Let's talk about integrands with vertical asymptotes. Another type of improper integral that can arise is when the integrand has a vertical asymptote or infinite discontinuity at a limit of integration or at a point on the interval of integration. We apply a similar technique as in previous examples of integrating over an altered interval before taking a limit. Example 4 says investigate the convergence of the integral from 0 to 1 of 1 over the square root of x dx. The reason that we run into an issue here is that our function has a vertical asymptote at the lower limit of integration. So I can't really plug in 0 into my function. My function is undefined at x equals 0. So the way that we're going to do this is it's going to be kind of similar to previously, except now we're taking the limit as a approaches 0. I can't really plug in negative numbers, so I'm going to approach 0 from the right-hand side. And we're keeping the same integrand, but I'm going to rewrite it as negative 1/2 power instead of 1 over. And so now let's integrate this. We have the limit as a approaches 0 from the right-hand side of, and then if we take the antiderivative, we're going to get 2 times x to the 1/2 power, and we're evaluating this from x equals a to x equals 1. So we have 2 times the square root of 1 minus 2 times the square root of a. As a gets closer and closer to 0 from the right-hand side, this expression is also going to go to 0. So our final answer is 2 times the square root of 1, which is equal to 2. So it says investigate the convergence. We can say therefore our integral from 0 to 1 of 1 over the square root of x dx converges to 2. And that's our answer for this example. So integrals of functions that become infinite at a point within the interval of integration are called improper integrals of type 2. You can read below the 3 subcases. They're kind of similar to the 3 subcases we saw earlier in type 1 improper integrals. In each case, if the limit is finite, we say that the improper integral converges, just like last time, and that the limit is the value of the improper integral. If the limit fails to exist, the improper integral diverges. Example 5 says investigate the convergence of the integral from 0 to 1 of 1 over 1 minus x. Now, notice that our vertical asymptote is at our upper limit of integration this time, so now we're going to have the limit as b approaches 1 from the left-hand side of the integral from 0 to b of 1 over 1 minus x dx. So I'm going to use u substitution. I'm going to let u equal 1 minus x, and then du will equal negative dx, and negative du will equal dx. So this is now going to equal the limit as b approaches 1 from the left-hand side of the integral from u1 to u2 of negative 1 over u du Let's go ahead and sub back in our x now. Okay, so now we can plug in our limits of integration. So we have the negative natural log of the absolute value of 1 minus b, and this would become plus the natural log of 1 minus 0, which is 1. And as we know, the natural log of 1 is 0. So now I'm just plugging in values for b that are approaching 1 from the left-hand side. So for example, I could plug in 0.9, 0.99, 0.9999, and that means that the inside of our natural logarithm is approaching 0. And from earlier, if you don't remember, here's 1 comma 0. Our graph looks something like that for y equals the natural log of x. So as the input of the natural log gets closer to 0, the output gets closer to negative infinity. So we have this negative sign from here, and then the limit as b approaches 1 from the left-hand side is approaching negative infinity, and so this goes off to infinity. The conclusion we can make then is therefore the original integral diverges. And there's our answer.